Alright, so in this example I'm going to go through how to work through the rational root theorem, and I'm going to give you a way to come up with your own examples so you can practice this technique on your own. So you got to consider that this is for going from unfactored form, which we call standard form, and we have something like this: f of x equal to, let's just make one up, 10x to the 6 minus 5x cubed plus x squared plus 1. So say we want to go from this right here into a product. And so we're thinking factoring right here from standard form. For polynomials like this, we don't have such an easy technique because they have all these other terms in between in the middle. We can't just write it as two factors. This one actually has 6 complex roots. So we have this process called the rational root theorem. So I'm going to come up with a polynomial, and I'm going to start with it in factored form. And let's even add one more on there. Let's add x minus 1. Alright, so I'm going to expand both of these, which is good practice. That's x squared plus x minus 6. And I'm going to multiply that by x squared minus 1, because this is a difference of squares. So that's going to be x to the 4th minus x squared plus x cubed minus x minus 6x squared plus 6, which gives me our polynomial in expanded form. X to the 4th, that's an x squared, so I got plus x cubed minus 7x squared minus x plus 6. Okay, before I go any further, I'm going to check with Desmos and make sure that this is the correct function, so I'll post a screenshot on the next slide. Okay, so you can see here that I graphed both functions on Desmos, the factored form and the unfactored form, and I have the same function. So I do have the correct expanded form. So let's look at that polynomial. That is f of x equal to x to the 4th plus x cubed minus 7x squared minus x plus 6. So we're going to start off by using the rational root theorem. And the rational root theorem says that if there are any rational roots for this polynomial, they're of the form plus or minus the factors of the constant divided by the leading coefficient. And again, these are factors. And if we look at our constant right here, I'm going to put that on the top, so I'll use a different color here. We've got our plus or minus in front, and that it distributes to every single possibility that is coming up here. We have 1 is a factor of 6, 2 is a factor of 6, 3 is a factor of 6, and 6 is a factor of 6. And if I look at the leading coefficient, since this polynomial is in standard form, I could tell based off of the degree there is 4. I just have to have a 1 on the bottom. So there's all the different possible rational roots. And so just for right now, I'll list them all out. I got 1, I got negative 1, I got 2, I got negative 2, I got 3, negative 3, I have 6, I have negative 6. If I had another number in the denominator, like a 2, I'd have to account for each of those other combinations, like 3 over 2, or 1 over 2. But fortunately here, my coefficient is just 1. Okay, so now I need to use the process called synthetic division. So I'm going to start my synthetic division with a number that I choose from there. So I know one of the roots I know all the different roots of this polynomial, so let's pick one that we know isn't a root. And so it looks like 2 is a root, so negative 2 is not going to work. So I'm going to put negative 2 in here just to show you how you can tell if you don't find a root. I have to list the coefficients, and so I have 1x to the 4th, I have 1x cubed, I have negative 7x squared, I have negative x, and I have a positive 6. Synthetic division, I bring down the first number. It's 1. I multiply negative 2, and I add negative 1, positive 2, negative 5, 10, 9, negative 18, negative 12. Okay, that right there, that's my remainder. And we know it's not a 0, because if we don't get 0, then that's not the function value at that point, which means it's not the x-intercept, not what we're looking for. Okay, so it doesn't work. Let's try another example. Let's do one that actually does work, and that was 2. Again, listing the same coefficients, 1, 1, -7, -1, 6. Bringing down the first term, multiplying, adding, multiplying, adding, multiplying, adding, multiplying, and boom, I got 0. That's exactly what I want. So this means that I can take this polynomial here and write it as a product of a binomial, which is going to be x minus 2. That comes from up there. Remember, it's x minus a. And what's left is, well, I started with 1x to the 4th. Then I had x cubed, and so it's going to be 1 degree left if I factor a linear out. So x cubed plus 3x squared minus x minus 3 is what I'm left with. So x cubed plus 3x squared minus x minus 3. Now from here you got to keep going, but just note that there is a factoring technique that you could use here and be done with this problem instantly. So I'm going to do another number that we know is a 0. Another number we knew as a 0 was 1. I always recommend starting off with 1 or -1, and you can always graph the polynomial to see the actual zeros. Okay, well 1's going to work, and now I'm going to use these coefficients down here. 1, 3, -1, -3. 1, 3, -1, -3. And bring down the 1, multiply, add, multiply, add, multiply, add. Now, I have my original factor, x minus 2. Keep it in that orange color. I have my new factor, x minus 1. And now I started with a cubic, and so I'm going to jump down to a quadratic. X squared plus 4x plus 3. Again, this is all equal to 0, all equal to f of x, whatever you want to write there. I'll just be careful from here. You don't really have to keep going because I have a quadratic, and I have either the quadratic formula or I can factor that, and you should recognize that that is x plus 3, x plus 1. So there's my completed factored form, x minus 2, x plus 1, x plus 3, and x minus 1. All the roots of that polynomial.